Okay. So everybody except Lou, I guess, can hear me. But that's going to be a problem on Lou's side. So let's get started. I'm also trying a new way to record this, so hopefully the videos on YouTube are better as well. So last time we did some examples of using the principle of virtual work. And the principle of virtual work stated that the sum of the virtual works for a set of external forces from I to N, where you have capital N external forces, that is equal to 0 if the system is in static equilibrium. Okay? Where this delta R was a virtual displacement. We also introduced this concept of a generalized force, Qj, that was the sum from I equal 1 to N of the external forces dotted with the derivative, the partial derivative of the vector of where the force is applied. And we found that Qj, we did a few examples where we saw that Qj does not necessarily have the dimensions of force. In fact, the examples that we did, Qj had the dimensions of torque. And we found that it was equivalent to either set the virtual work equal to 0 or all components of the generalized force equal to 0. So we saw that this generalized force is a much more general concept than it is in vectorial mechanics. Sorry. So this was the problem of statics. And it's sort of the same thing that you would have done in same progression you would have done in first year undergrad physics, where you started with Newton's laws, and then you solved a bunch of problems where the sum of the forces equals 0, and find something about some force. Then after that, the next obvious step is how to generalize this to dynamics. So dynamics. So remember, statics in the vectorial mechanics is basically given by the scenario where the sum of the forces equals 0. All right. And in dynamics, we would say that the sum of the forces is equal to ma. And so what we'll start with today is what's called D'Alembert's principle. And so D'Alembert's principle starts off, let's pretend there's only one force for now. It starts off with Newton's second law in the dynamics case. So the whole principle, the whole point of using D'Alembert's principle is to now address dynamics. So when stuff is moving because of forces. And D'Alembert's principle is very simple. You take Newton's law and you just rearrange it. And that's D'Alembert's principle. Pure genius. So it doesn't sound that clever to rearrange Newton's second law and give it a new name and claim that it's a genius way of doing mechanics. So let's look at it a little bit more. Let's introduce a new thing called I, arbitrarily I, a new vector I, which I'm going to call set equal to minus ma. I'm going to call that a force of inertia. So D'Alembert's principle really says that the applied force F plus this force of inertia, which has the correct dimensions to be called force, is equal to 0. Okay, so this is also not mind-blowing. But the key thing to note here is that this kind of looks like a statics problem with the, let's call it the extra force I. And so what's really key here in D'Alembert's principle is that you can recognize that you can write Newton's second law this way and treat this ma term as a new force, and then you effectively transform the dynamics problem to a statics problem. And that's really the key thing, is that you can do all of the things of statics to dynamical situations as long as you include this additional inertia force. So another way to think about it is, so you're in a car and you go around a curve and then you're pushed to the outside of the car. So what D'Alembert's principle is saying is that instead of studying motions of things in the car as an accelerated frame of reference, you can pretend you're in the frame of reference that's accelerated and moving with the car, and then you have to add in this additional force to account for weird motions that you would see in an accelerated car. And that's exactly the same thing that arises when you try to, the Coriolis force, for example, right? If you try to shoot a cannonball across the Earth or for a long distance, because the Earth is actually a rotating reference frame, the cannonball will not go in a straight line. It will actually deviate because of this Coriolis force. And this Coriolis force is exactly the same thing as this force of inertia. It arises through the same mechanism. Let's call this page 1. So, with D'Alembert's principle, we can now apply the formalism that we just did with the principle of virtual work for statics to the realm of dynamics. So now it's a much more general concept that the total virtual work should be equal to 0, right? D'Alembert's principle also holds in statics when ma equals 0. So very generally, one can write that the virtual work on a system of I particles so that's given by the sum of the forces dotted with the virtual displacement vector of every particle. So just to be clear here, we have n particles, and Fi is then the net applied force on particle I. And then big I sub little I. So the big I is the force of inertia of particle I. And so we could introduce, if we wanted, an effective force. That's a script F. To be the applied force plus the force of inertia of particle I. And then the principle of virtual work, which is now D'Alembert's principle, is that the sum over all the particles of this effective force is equal to 0. And that's now valid for both statics and for dynamic problems. This effective force contains both the applied force and this force of inertia that we've introduced. The net applied force on the particles could in principle also include forces of constraint. But as we saw in most cases, these forces of constraint or these internal forces do no virtual work, and that will still be true. And delta R is again a virtual displacement that is in harmony with the allowed constraints. Okay. So now we want to be able to put this in a way that we can, solve problems. When we write the principle of virtual work this way, because in principle there could be constraints, so the RIs are not independent. So this does not mean necessarily that the FIs are 0. Because the delta RI vectors are not independent. So of course what we want to do is to transform this back into generalized coordinates so that the delta RIs are equal to 0 or can be varied independently so that the FIs, or whatever we end up with, is identically 0. So it's exactly the same thing that we did for the principle of virtual work when we converted it to a generalized force. Once we had a generalized force dotted with a generalized coordinate, the coordinates can be varied independently, and so the generalized forces are identically 0. So we basically want to do the same thing, except it's going to be much more complicated this time around. And you'll see why in a second. So let's write out the virtual work again. I'm not going to use the script F because I'm going to separate them out. So the total virtual work is the sum over n particles of the applied force plus the inertial force of particle I dotted with delta Ri. And that's got to be equal to 0. So if I expand this out, that's in two terms, so that's going to be the sum of I equal 1 to n of fi dotted with delta ri plus the sum of I equal to 1 to n of the I dotted with the delta ri. Now this first term here, this is exactly the same term that we worked with when we did the principle of virtual work, right? And so we found that we can write that as the sum over of I equals, the sum of j equals 1 to little n, where n is the numbers of degrees of freedom, qj delta qj. Right? Where the qj, well, I just defined it again in the summary, right? It has the sum over I inside of it. And then the second term, I'm just going to rewrite here, and that's the one we're going to have to work with. So this term here is going to be a little bit more annoying to work with. So for the next hour, pretty much, we're going to work on the second term in this equation. And it's not going to be as easy to convert this. So the goal is to go from a sum over I equals 1 to n of I dotted with delta ri to some sum over j equals 1 to little n, the number of degrees of freedom, something with delta qj's in it. Okay. So let's look at this term. So we have the sum of I equals 1 to n of I sub I dotted with delta ri. Now remember the definition of I sub I, which was equal to m I a I. All right, that was from the Newton's law term. And to use our notation, right, we want to write this as mi ri vector double dot. Right, because acceleration is just 2 times the time derivative of the position vector. So we can rewrite this as minus the sum of I equals 1 to n, big N, of mi ri vector double dot dotted with delta ri. And now we want to go into, we want to have delta q's instead of delta r's. So this is equal to the sum of, so minus the sum of I equals 1 to n of mi ri double dot dotted with, and now we'll put the sum in from j equals 1 to little n of di ri vector by di qj delta qj. but we're not there yet. So we do have the delta QJs in there, but we have this RI double dot in there. And the whole rest of the lecture pretty much is going to be how to get rid of the R double dot. So let's remember this equation here. All right. Let me box it in red. And in a while, we'll get back to it. So we'll start by considering an identity. So consider taking, for some reason, the time derivative, the total time derivative of mi ri dot, so only with one dot, dotted with the sum of j equals 1 to little n of di ri vector by di qj delta qj. All right. So we just use the product rule for derivatives here, right? So the things that depend on t, let me write that on the side just so we know that the ri are functions of t, and the qj's are functions of t's, right? The m's don't depend on t. So if I apply the product rule here, I get the derivative of the first term with respect to time. How did I write this out? Which is mi ri vector double dot times the second term unchanged, the sum of j equals 1 to n di ri vector by di qj delta qj, plus the second term. So then this is the first thing unchanged, so that's mi ri dot times the time derivative of the second term. Let's write out explicitly. It's d by dt of the sum of j equals 1 to n of di ri vector by di qj delta qj. Now there's nothing that prevents me from bringing this delta t inside of the sum, and it also commutes with the di by di qj, right? So the first term I'm going to leave unchanged, mi ri double dot sum j equals 1 to n of di ri by di qj delta qj, plus, and now the second term, so I have mi ri dot, and now bringing the derivative inside, I have the sum of j equals 1 to little n. I'm going to bring the derivative in front of the di by di qj. So I have di by di qj, and then I have d by dt of ri, and that I can just write as ri dot delta qj. Okay? So now note that the first term in here is the term in red, right? So let's box that term in red. So we have the first term here, the term that's written after the words consider. and that's equal to the last line here, right? So in every single term, there is a sum over j from 1 to little n, right? Each term has it. So it's here, it's here, and it's here. And inside of that sum, there is always a delta qj that goes with the sum term, right? So for this equation to be true, I can move the sum out of the front of each term, right? So I could put the sum term in front of each of these terms, and then each term has to be equal for each j. So I'm going to rearrange this equation now, and I'm going to drop the sum over j and the delta qj. I'm also going to rearrange it so the red term is on a side by itself. So we have, without the sum, this first term here is MIRI double dot. I'm not going to write the sum term or the delta qj. So then I just have di ri by di qj. Right, that's the first term. Okay. Well, this class is too long, an hour and a half anyway, so it's good that we have these technical breaks. Time to gather our minds. The IT guys are aware of this. Just give people a minute to recompose. All right, so hopefully, the IT guys did contact the company that's running the server, so hopefully they sort this out for next week. Otherwise, we're going to have to try and find a different solution. Okay, so let's remind ourselves of what we were doing here. We were modifying this sum over the forces of inertia. We got this red term at the top here when we converted it to delta qj's, but we're left with this ri double dot, which we need to get rid of. We considered this identity, or we do d by dt of some term, and then we used the product rule, and we found that d by dt of this term, one of the terms is the red term that we were interested in, plus some other term. And then we started rewriting this, putting the red term on the left. Then the second term was the term that we expanded, and now we're left to write the third term. We also noted that all three terms have a sum over j and a delta qj. And so just so we don't have to write it each time, we're not writing the sum in. But it's true that the equation or the identity is true for each term. So we don't need to write out the sum over j and delta qj. So the first term, so I rearranged there, right? We have the d by dt of the whole thing equals the red term plus the last term. I put the red term on the left-hand side, and then I'm left to write the first term and minus mi, so I'm now writing this term over here, mi ri dot, mi, yes, ri dot, dotted with d by dqj of ri dot. Okay? So we're getting there. So this is our red term here. Maybe it helps if I keep putting it in red. Now consider the following identity. Consider taking d by dqj of ri vectored dot. All right, that's the term that we have, the last term we have in the equation above. So that's the same as di by dqj. If I write now ri, that's the same as the sum of the notes. It's mathematically not correct. It should be a k. That is the same as the sum of k equals 1 to little n of di ri by di qk dot plus the, or dot, sorry, has to be a partial derivative, di ri by di t. I just used the definition of ri dot, right? Recall that ri dot is equal to di ri by di q1 dot plus di ri di q2 dot plus etc. qn term, and then the last term was a di r by di t term. All right, that's all I did when I expanded my ri here, ri dot. So now if I take the d by dqj inside of there, right? So I get the sum of I equals, or sorry, k equals 1 to n of di by di qj of looks like this time I was the only one that was kicked out. Why is it not sharing the right thing? Sharing. No. Share. Okay, well, as I was saying, the last term doesn't explicitly depend on Qj. So di by di Qj as the last term is 0, right? Now the first term is also going to be 0. The second term, so the first term in the parentheses does not depend on Qj except when k equals j, right? So this thing here, in the end, the sum is going to drop because any term with k not equal to j will disappear, and what we find is we are left with di by di Qj of di r I oh, I made a mistake. It's not a big mistake, but it changes all of the equations. I'm sorry. The first, we're taking the partial derivative with respect to di Qj dot. So this di Qj at the front here should always have a dot in it. So far we haven't used that property. So it's just a matter of adding dots to all your equations. Okay? And so for the last term, the derivative of by Qj dot of di Ri by di Qk dot is only 0, is only non-zero when k equals j, right? So then it's di by di Qj dot of this di Ri vector by di Qj dot. And so the derivative, the partial derivative with respect to Qj dot of this thing is di Ri vector by di Qj, right? The derivative of the thing in parenthesis, it's the term that multiplies the Qj dot. So it's the di Ri by di Qj. Sorry for forgetting the dot in the beginning. And so if I rewrite this on the next page, the energy that we've just derived here is that di Ri dot by di Qj dot is equal to di Ri by di Qj. So the thing on the left has dots, and the thing on the right is the same thing without the dots. And what this really tells us is that given the transformation equations for the coordinates, the velocities transform in the same way. So we put that back into our equation that we had before. So the equation that we had before is that mi ri double dot di Ri by di Qj. That's the term that's true for each j, right? We found that we could write as d by dt of mi ri dotted with di Ri by di Qj minus mi ri dotted with di Ri dot by di Qj. So what we're going to do is we're going to change this term here using that identity. And so that gives us d by dt of mi ri vector now dotted with di ri dot by di qj dot. We're going to dot up here. The second term is minus mi ri dot dotted with di ri by di qj. All right. I'll consider the following identity. Consider di by di qj dot of ri dot, or ri dot, yes, dotted with ri dot. All right, so it's di by di qj dot of a scalar product of ri dot with itself. So applying the product rule, that is the same as ri dot dotted with d by d, or di by di qj of ri dot, plus, again, the same term, right, except now, if I write out explicitly, is di by di ri dot by di qj dotted with ri dot. Okay, so that's 2 times the same term. So that's 2 times ri dot dotted with di ri dot by di qj dot. I forgot the dots on the di qj's. Okay. And so the term there that we just wrote is what appeared in the equation above. We had an ri forgot the dot up here as well. Right here, there should be some dots that I forgot to copy over. And so you can see that this term here is similar to this term here. So I can write that term out as ri dot dotted with di ri dot by di qj dot is equal to a half. So I'm just moving the 2 to the other side there, of di by di qj dot of ri dot dotted with ri dot. And so, of course, a vector dotted with itself is just the norm of the vector squared, right? So that's just a half of di by di qj ri dot squared, where I've just used that ri vector dot with ri vector dot is equal to ri squared, the scalar. So similarly, the exact same math, you can write that ri dot dotted with di ri dot by di qj is equal to a half di by di qj of Ri dot squared. And that's the second term that we had here. Okay. Let me just write similarly. Okay, so we're ready to put that back into our red box term. Am I going to need a new page? No, I can write it all on one page. So the term we were interested in was mi ri double dot di ri by di qj. And so that's equal to d by dt of this first term we have up here, right? And then it's going to be the second term. So the first term, which is the red term, that is mi times a half di by di qj dot ri dot squared. All right, that's this red term. And then it's minus the blue term, and that's mi a half di by di qj of ri dot squared. So it's nice because we've eliminated the vectors. That was the point of this last little manipulation. Now the mi does not depend on the qj dot. The mi is a constant. So let's write this a little bit differently. Let's write this as d by dt of, and the half is obviously a constant as well. So that's di by di qj dot of a half mi ri dot squared minus, do the same thing on the other term, di by di qj of a half mi ri dot squared. Okay. 4. So let me introduce a new quantity. I'm going to call it t. I'm going to define it to be a half mi ri dot squared. And so what we found is that our term that we were working with, mi ri double dot times dotted with di ri by di qj is equal to d by dt of di t, so this is the ti, di ti by di qj dot minus di ti by di qj. And so you may recognize this ti, and that's the kinetic energy of particle I. Right? Ri dot is d by dt of the position vector of particle I. So it's speed. So it's a speed squared. So it's like the v squared, and of course the half mi v squared is what you get for kinetic energy. So it's a little bit interesting that all of a sudden kinetic energy came into play here. And remember, what we're doing here is we're modifying that virtual work term that was associated with the force of inertia. There's a question from Lou. A bit confused about I, J, K. Could you explain the three of them again? So that's going to be in the previous. Where did we have the K's? Even earlier than me. Okay. So there are capital N particles, and we've used the index R to go over the different particles. And each particle we've assigned a net force Fi. So each particle could in principle have multiple forces acting on it, but the net force, the net applied force, we've labeled with I as well. So each particle I has a force I. So I goes from 1 to big N. The J's go from 1 to little n, and they're the loop over the sum over the degrees of freedom. So there are there are little n generalized coordinates, and we label those generalized coordinates Qj. And the general strategy has been to expand any position vector r, whether it be r1, r2, or ri, in terms of a sum over n generalized coordinates Qj. Now, one point here in this equation, we did that same expansion of the vector r over the n generalized coordinates. But we already were using the index j because we're looking at the j term of the sum, so I had to introduce an extra index k, but k goes over the same range of indices from 1 to little n. It's kind of like when you write an integral, you shouldn't write the same variable as the dx and then have the integral go from 0 to x, right? Let me just do this on a scratch page here. I'm going to erase this in a second, but in principle, you shouldn't write f of x equals 0 to x of f of x dx, right? You shouldn't write that because that's wrong. What you should write is f of x is equal to the integral from 0 to x of f of x prime dx prime. So it's exactly the same thing with the sum. I can't use the same x inside and outside of the sum, so I can't use j and k inside and outside of the sum. Yeah. So far what we've used is, okay, well, I think you said you got it, so that's not there. All right, so back to our D'Alembert's principle. So we got a little bit sidetracked, right? But remember, what we wanted to do was the sum of this force of inertia I dotted with delta Ri, right? And that's I equals 1 to n. Oops, I can write that later. Right, and so we found initially that was equal to minus the sum from I equals 1 to n of mi ri double dotted with delta ri. And then that's equal to the minus the sum of I equals 1 to capital N of mi ri double dot. And now I'm converting the delta Ri so I can have it in Qj. So now I have to put a sum of j equals 1 to little n of the di Ri's by di Qj delta Qj. Now what we did is we found that this we could rewrite as minus the sum of I equals 1 to big N. I'm going to take the sum of j's out. So it's the sum of j equals 1 to little n of mi ri double dot dotted with di ri by di qj by delta times delta qj. And we found that this thing here we could write as the kinetic energy. So we found that this we could write as d by dt of di ti by di qj dot minus di ti by di qj. And we have the delta qj at the end. Now, there's nothing that prevents me from swapping the order of the sums over I and j and bringing the sum over I inside these terms. And so to write this explicitly, that's minus the sum of j equals 1 to n of d by dt of di by, now it's the sum over I equals 1 to big N of the ti by di qj dot minus di by, again, the sum of the over I equals 1 to big N of the ti di qj delta qj. Now let me introduce t to be the sum from I equals 1 to big N of the ti. So we can call that the total kinetic energy of the system. Oops, that should be quotation mark. And so what we find is that this whole contraption here is equal to minus the sum of j equals 1 to n of d by dt of di capital T by di qj dot minus di capital T by di qj delta qj. So our total virtual work, remember it had two terms, delta W was equal to the sum of the Fi plus the inertial forces I dotted with delta Ri. And that's got to equal to 0. And the first term, thus the sum of I equals 1 to n. We know that the sum over the external forces we could write as the sum of j equals 1 to n of qj delta qj. And we just found now that the second term we can write as minus the sum from j equals 1 to little n of d by dt of di t by di qj dot minus di t by di qj delta qj. Now, the delta qj's can be varied independently because they're generalized coordinates. And so for this sum to be 0, the term that's not the delta qj must identically be 0. So if I factor out the delta qj, to be really explicit, I have the sum of j equals 1 to little n of qj minus d by dt of di t by di qj qj dot minus di, that's going to be put a bracket here, minus di by di capital T by di qj, close parentheses, delta qj. So now this must equal 0 for all qj. And since the qj's can be varied independently of each other, that means the term in parentheses must be 0. And so we get our results that d by dt of di capital T by di qj dot minus di t by di qj is equal to capital Qj. And that's the form that's really the result. So T is the total kinetic energy. So let's finish this up by recalling one of our results from variational calculus. So recall from variational calculus at some point we were interested in finding the stationary values of some integral of some function L that depended on the qi dots and the t's by dt, subject to some constraint equation where you had maybe a sum, you had k different constraint equations where you had a function little f of the generalized coordinates and we found that the condition for this to be stationary was given by the Euler-Lagrange equation, and that was d by dt of di L by di Q dot J minus di L by di Qj was equal to some big Qj, where we found that Qj, the big Qj, was given by the sum from I equals 1 to big N. Oops. It was the lambdas. Oh, there it is, sorry. It's not to big N, it's to K. So for the K constraint equations, we had a lambda K, the Lagrange multiplier, times di Fi by di Qj. Right? So we had K constraints, and we're asked to find the stationary value of some integral L, some function that depends on Qi dots and T. and we found this Euler-Lagrange equation solves the problem. So compare this to what we just derived from D'Alembert's principle. It looks very similar, right? Instead of L, we had called it T. And then we didn't have constraints. Rather, we had these forces. QJs are the generalized forces. So this is similar to D'Alembert's principle, where we want to find the stationary value of some integral of the kinetic energy over time. And then the generalized forces, Q, are somehow related to some constraint equation that we haven't really thought about yet. But the mathematics of this variational problem, somehow the generalized forces have the same role as these constraints that we did very arbitrarily when we're doing the mathematics of it. So I sort of leave you to ponder that until next week. Any questions? Okay, so if there's no questions, we'll meet again on Monday. Thanks everyone, and hopefully the technical stuff gets better. Bye.